Justin Miller, Oxnard College Physics here. We are going to tighten things up, so to say, and start looking at some more forces. In particular, we want to look at force of tension. So let's just go ahead and do this. Forces of tension. Generally, forces make people tense to begin with, to some degree, but we want to talk about a particular type of tension, and that is a force transmitted via rope, string, cord, etc. Via a rope, string, cord, etc. So it's a contact force because generally when you have something tied to a rope, string, or cord, it's contacting that something, the mass under consideration, and it can exert a force on it. So what we want to do is kind of give that a little bit of a look and kind of model something out so we understand how forces of tension work. They're basically another type of applied force, contact force, so to say, and that's it. So what can we do here? Well, we could do this. I've got a 1 kilogram mass right here, and I've got this little handy string right here that, well, is in contact with this mass, right? There's a force of tension in this string. This string is exerting a force on this mass here. How do I know that? Because the net force on this mass is 0, that's right. It is, we'll keep it from spinning, and stationary. So being that it's stationary, net force has to be equal to 0, there's no acceleration. You know that gravity is acting on it, right? Gravity's pulling it down, so this string must be pulling it up. How does it pull it up? Because there's a force of tension on it. Transmits the force. I'm not worried about my hand here, my thumb. We're not taking into account or really looking at the force that my hand exerts on the string. We're more concerned about this mass right here. So we ask ourselves, what's acting on it? We've got gravity's acting on it, the field force. We've got one contact force, one thing touching it, and that's the string. So that's all that we've got. So I can actually see a couple things here by taking a handy scale that is in newtons. I can start looking at, well, the weight of the object in newtons. Well, check this out. It's just about 10. It's like 9.8 or something, 9.8 newtons. Why do I get that many newtons for it? Well, we've got gravity's pulling this down, and well, ultimately is pulling down on this little hanger just as well. This total mass is transmitting a force of tension via the string onto this, which is connected with some mechanism in there, which produces a deflection that's scaled to read the object's weight in newtons. So it says 9.8. Well, what does that mean? Well, that's the force of gravity, right? That's the object's weight in newtons. Gravity pulls this down with an mg. M is 1 kilogram, g is 9.8 meters per second squared. So what is the force of gravity acting on this mass? mg, it's 9.8 newtons. And because this mass is at rest, well, this has to ultimately bear that object's weight, react to it, and measures it out, 9.8. So, again, we're more concerned about this mass right here, but this is just giving us the ability to see some of the things that could happen. What happens if I start accelerating this object upward? Well, watch what happens when I give it a rapid acceleration upward. What happens to this needle here? Whoa, I have to do that a little bit slower, but you should see that the needle undergoes some deflection this way. All of a sudden it seems like the object weighs more. And then when I'm stopping it, the object deflects this way, like the object weighs less. I can get the same sort of effect by lowering this object, accelerating it downward. If I start accelerating it downward, it's like the object weighs less all of a sudden. But then when I stop it and, well, I'm ultimately producing an acceleration in the opposite direction that it's moving, it's like the object weighs more. You get a similar effect on an elevator if you're standing on a scale, right? You're standing on a scale in an elevator, and it's kind of reading like the normal force. And what happens when the elevator starts going up, accelerating for that brief moment, all of a sudden you feel this, ooh, like you're heavier. When it's stopping, while it's going up, it feels like, oh, you're lighter. You get the same thing when it's going down. When it starts going down, you feel lighter all of a sudden. And when it stops, or when it's coming to a stop as it's going down, you feel like you're heavier. Get the same sort of reaction here. It's force of tension. But anyways, this is what we want to kind of look at. And to see, it's just another force that can act on objects. I can start pulling objects. I can start going upward, going in different directions, swinging objects. There's all sorts of things that I can do with a rope, string, or cord acting on an object. I just want to get particulars down. So we will use T hat to denote a force of tension acting on an object. So what can we do? Well, there's lots of things that we could do. We could take some object that's on some horizontal surface, and I can say that we've got some rope here, and that we are going to pull on this object with some force of tension T hat. So I don't need to write that I'm pulling over here. All I need to note is what is that force of tension that's transmitted through the string? And then I can start to get the idea, well, yeah, if you pull on it hard enough, it's going to start accelerating. There may be some other forces. Well, there would be in this case. There would be a normal force and a force due to gravity at very least. There could be some other things going on, but this is how we'd start to draw stuff out. I could have something like this. I've got some, this should be a mass. Got some mass M. I've got some rope here, and maybe it's tied to the ceiling. What do we have? Well, we can start to draw out the forces that are acting on this. In this case, I could say, hey, we've got this force of tension that's upward, and this force of gravity, which is downward. Assuming that this mass is remaining at rest, those two would have equal magnitudes, opposite directions. So the force of tension is ultimately responsible for suspending this object. What happens if we cut the rope? We cut the rope, tension goes to zero, the object is just subject to the gravitational force and would be in free fall. And that would be that. What happens if we pull on this object harder? The force of tension would have to respond and pull back upward harder in order to keep this object there. If we pull hard enough, maybe the rope breaks. There's some sort of maximum force that the rope, string, or cord can build up to, much like we had with the normal force. So we've got some similarities here, but it's a different system. We just got to get used to forces of tension. So really the best way to get used to them is just start looking at a couple little problems and kind of go from there. So we'll see them in many more problems. I just want to get the idea of how to approach systems with a force of tension, and that'll be that. So let us go ahead, look at a nice little problem. Here's the problem. All right, so we're going to take ourselves a 40 kilogram mass and say that it's suspended at rest via a string. So it's kind of what we just drew out. So we're having some particulars here. So we'll take our mass here. We've got some string or rope, whatever. And say that the velocity of this mass is 0. The mass itself is equal to 40 kilograms. And we are asked, what is the force of tension? Well, in order to start understanding that force of tension, we've got to analyze the system. We ask ourselves what forces are acting on it, because we know that the net force produces the acceleration of the mass, right? And since this mass is held at rest, we have to have that the acceleration is 0. So we can go ahead and draw a little force diagram and get, hey, we've got some force of tension there, and we've also got some force of gravity there. Any other forces in here? Nothing else is stated. We got a field force. We got to assume that we're on Earth, And then we got the force of tension, or have the force of tension, that is responsible for suspending this object. So we've got, what does the net force produce? Well, the net force produces the acceleration of the mass, which has to again be equal to 0, since a hat is equal to 0. That comes again from the object being stationary. We also have, what is the net force composed of? And, well, we've got two forces there. We've got a T hat and F sub G hat. So we go ahead and say, hey, that's the force of tension plus the force due to gravity. Net force equals, net force is composed of. At that, we can go ahead and say, well, T hat plus F sub G hat must be equal to 0. T hat plus F sub G hat is equal to 0. From there, what do? Well, we could solve this out for T hat, right? T hat is equal to negative F sub G hat. The force of tension is equal in magnitude, opposite direction to the force due to gravity. So, what do? Well, we know that the gravitational force in general, F sub G hat, is equal to negative mg J hat. So we can go ahead and stick that in for the force due to gravity and get ourselves that T hat is then equal to minus negative mg J hat. Well, the minus minus cancels out, and we've got ourselves T hat is equal to mg J hat, which is then equal to 40 kilograms times 9.8 meters per second squared in the J hat direction, giving us that the force of tension in that rope, 9.8 times a 40, gives us 392 newtons J hat. So in this particular case, since the object's stationary, the force of tension is equivalent to the object's weight. The string has to bear the weight of the object. It has to hold the object up. That's it. So we got 392 newtons, which is substantiated by the 40 kilograms under the action of the gravitational acceleration. Alrighty then. So let's go on to part B and say, you know what? We're going to change this a little bit. We're going to say this object is actually moving upward at a constant rate. Oh, what now? So we're going to take this object, and I can only do this over a very small distance, but we can say, oh, it's just moving up at a nice smooth rate. So let's look at this needle while it's actually moving at a nice smooth rate. And the needle stays pretty stationary as long as I'm not kind of jerking around. At any rate, what do we have with this? Well, we've got part B, number 1. B is equal to constant, then A hat is equal to, well, if the velocity is constant, then the acceleration has to be equal to 0. There is no change in the velocity with respect to time. That means no acceleration. So where are we at then? Well, we're back here. We've still got the same two forces acting on the object, the force of tension and the force due to gravity. And we got that the net force has to be equal to 0, and the net force is the force of tension plus the force due to gravity. So net force produces no acceleration, and the net force is the vector sum of the forces acting on the object under consideration. And well, we go through this same thing, same result, same condition. Same result. The force of tension would be equal to 392 newtons in the J hat direction. So we did something like that with the normal force, something sliding across horizontal surfaces at a constant rate. You can also kind of get the idea of this by what if you were on an elevator going upward at a constant rate or downward at a constant rate. You feel pretty normal, right? It's only when you undergo a change in velocity you feel lighter or heavier. When you're moving at a constant rate, there is no change. You're driving in your car at a constant rate, you don't feel like something's pushing you back or pulling you forward like you do when you're accelerating or stopping, right? It's only when those changes in velocity occur is there an acceleration that correlates with some non-zero net force. So that's it. Let's move on to a part C. Part C gets a little bit more fun. We actually do something. We're going to take this object now and we are going to accelerate it upward at a rate of 3 meters per second squared. Now let A hat equal 3 meters per second squared J hat. So we've got an upward acceleration and we want to know what is the end result of this. So I'll just go ahead and switch boards here, switch colors as well. Go over to a part C. So now we do not have that the acceleration is 0, right? We've got this to start with. The net force produces the acceleration of the mass. And the net force is composed of all the forces acting. Well, it's just still the same two forces acting on this mass. We weren't told that there's another force that's making this happen. It's definitely not the gravitational force making it accelerate upward. It has to be the force of tension acting on it, right? So let's check that out. We've still got the force of tension acting plus the force due to gravity. Great. So net force produces, net force is composed of. With these, we've got ourselves that T hat plus F sub G hat must be equal to MA hat. There's a nice vector relationship between the forces and the overall acceleration being produced. So what do we want to do with this? Again, we want to solve this for the tension. What's the tension in the rope now? So we can go ahead and get everything to one side except the force of tension. And write ourselves that T hat is equal to MA hat minus F sub G hat. So if we could solve that out, that is if we know what A hat and F sub G hat are, we're good, we're gold. So the question is, do we know those? And the answer is, of course we do. We know what the force of gravity is, that's just mg hat, or negative mgj hat. And A hat, we're told specifically, that's 3 meters per second squared. So we can go ahead and put those values in, right? We've now got the T hat is going to be equal to, this is 40 kilograms, 40 kilograms multiplied by 3 meters per second squared. J hat, this is a vector. You need to treat it like a vector here. So it's 3 meters per second squared J hat. And then we've got minus F sub G hat. Well, F sub G hat itself is negative mg J hat, right? So I'm just going to put that in, negative 40 kilograms times 9.8 meters per second squared J hat. So negative mg J hat, kind of expanded out, and it's minus that. So those two minus signs or negative signs are going to cancel each other out and make this positive, and we're going to get this. T hat is going to be equal to, this is going to be 120 newtons J hat. 120 newtons J hat. And this, well, we've already computed this. That's just the weight of the object, which is going to be the 392 newtons plus 392 newtons J hat. So what do we have with the force of tension now? Well, we're going to get ourselves, what, 512? T hat is equal to 512 newtons in the J hat direction. So note something here. In order to accelerate this object upward at 3 meters per second squared, the force of tension transmitted via the rope had to increase to produce that acceleration, had to increase from just bearing the weight of the object to producing a change in the object's motion as well. Required an extra 120 newtons of force being transmitted through that, which results in, hey, that string has to bear 512 newtons of apparent weight. I want to say force. If it can't produce that much force, snaps, or undergoes some deformation, something like that. But that's what we've got here. All right, let's do one last thing. Let's say we actually want this object to accelerate downward at a rate of 5 meters per second squared under the criteria that we will keep the tension directed the same way. So in that we're gonna take this object. Whoa, that's not gonna work out too good. We'll go like this. 50 grand. So we're gonna take the object and now we're gonna descend it. And what happens is it descends as we accelerate it downward, the deflection of the needle lessens, right? Because the force that's being transmitted via this has to be less. So I kind of took the middleman out, the string there, but that's okay. Whew, that was almost my toe. That would have been bad news. Anyways, this is what I want to do. Figure out what that force of tension is now. And I think we can do it right over in this little spot. Let's do it with some blue, shall we? So D, change this. Now we're going to say that this is negative 5 meters per second squared j hat. So the negative j hat direction says that this object will be accelerating downward. And that is for part D. So D, I'll just write it here. A is equal to negative 5 meters per second squared j hat. And what do? We do the same thing that we did right here. You know what? We've still got that the net force produces the acceleration of the mass, and the net force is a culmination of the force of tension and the force due to gravity. Thus, the force of tension plus the force due to gravity must be equal to the mass times the acceleration. And then we can go ahead and solve that for the force of tension. T hat is equal to A hat minus F sub G hat. So that's the same exact thing that we got right here, right? Well, up until here, it's fairly arbitrary. We haven't put any values. We've just analyzed the same system with the same forces in general acting, but we've changed the outcome. Thus, we've changed one of the forces is doing. Anyways, we've got this. Just put in our stuff, right? We've got the T hat is going to be equal to, well, M, again, is 40 kilograms. A, however, now is negative 5 meters per second squared, j hat. And then we've got negative minus mg j hat, or minus negative mg j hat, which ends up being this right here, right? Minus minus ends up being plus 392 newtons. So we'll do plus 392 newtons j hat. This, however, turns out to be negative. So we've got ourselves the T hat is equal to negative 200 newtons j hat plus 392 newtons j hat, which gives us the grand total of, let's get ourselves 120. Nope, sorry. Messing this up. 192 newtons j hat. So now the force of tension doesn't have to exert such a great force. It doesn't have to bear the entire object's weight of 392 newtons. It only has to do a fractional value of that because we're letting gravity do some of the pulling down now, allowing the object to accelerate downward. So that's pretty much what we've got going on here. Draw diagrams. Net force produces the acceleration of the mass. Net force is composed of the vector sum of all forces acting. In one dimension, not that bad. Once you start getting into 2 dimensions, you got to break things up into x and y directions. But it's kind of the same thing you'll see over and over. It just is a matter of understanding the forces that are acting and being able to compose all of the relations between things and solve for what's being asked for. That takes time. Takes some time. Do it though. All right. So yeah, we'll leave it at that for now. Come back and do some more stuff in a while. Be well. Take care.